this binomial distribution worksheet. So the first part, the bag contains 4 gold balls and 6 silver balls. Don't laugh. 2 balls are drawn at random from the bag with replacement. Very, very, very important. So first binomial is always with replacement, because the odds can't change. So if you do a binomial type problem, it's always gonna be with replacement. Now they're never gonna tell you it's binomial. So how do you know it's a binomial question? It's actually not this. This is not the binomial part of it. This is just the This is like binomial distribution. This is the probability distribution part of it. It's right here. I see exactly, at most, I know it's a binomial question. Over here, same idea, right? At least one, get at least one, exactly, at least, at less than. All that stuff screams to me binomial distribution problem. So just get that out of the way first. Okay, now. So first question is actually more of, like I talked about, it's more of a binomial probability distribution question. Let X be the number of gold balls drawn from the bag. So here's the thing. If you remember me, when I do probability distributions, I like to make a box. Or we have our X, and we have our probability. So my X here is let X be the number of gold balls drawn from the bag. Now remember, we're only drawing 2 balls. So my odds are I could get 1 gold ball, 0 gold balls. Why I say 1, I refer to 0. So 0 gold balls, 1 gold ball, or 2 gold balls. That's it. Don't laugh. Right, so that's all we're doing. We're drawing 2 things from the box. We're drawing 2 things. So what's the odds of getting the gold ones? You could get 0 of them, 1 of them, or 2 of them. Let's actually find the probabilities, right? So gold and silver, so 4 and 6, so it's 10 total. So odds of getting gold are 4 out of 10. Odds of getting silver are 6 out of 10. If you really want, you can make this a tree diagram. You don't have to, but you could. Right, here's my little person drawing balls from a bag. That's probably my worst stick figure ever. Gold and silver. Gold is 4 out of 10. Silver is 6 out of 10. And then you do it again. Now remember, it is with replacement, so none of the odds change. 6, 10. 4, 10, 6, 10. If you're saying the wrong words, but writing the right thing, gold here would be 4, 10, and 6, 10. So what's odds of getting no gold balls? So that'd be silver, silver. So you go 6, 10, 6, 10. That's what this stands for. 0 just means you got silver both times. So 6 out of 10 times 6 out of 10. So 36 out of 100. You could reduce, but honestly, it's not worth the trouble. It's actually better this way. So odds you get no gold balls is 36 out of 100. Odds you get 1 gold ball. Now, how do you get 1? That could be gold and then silver and gold. So they add those 2 up. So this right here is gold silver plus silver gold. This will be 410 and 610 plus 610, 410. That'll give me 24 out of 100 plus 24 out of 100. So that'll give me 48 out of 100. Now, then they say find the expected value. Remember our expected value formula? That's just where you multiply n times p, but you have to take the sum of them. So I'm going to multiply 0 times this, 1 times that, 2 times that, add them all up. Well, first I got to find out what 2 is. So there's 2 ways of doing it. Remember, probability always equals 1, so you can do 1 minus these 2, or getting 2 gold balls is just gold. So 4 times 10, 4 over 10 times 4 out of 10, 16 out of 100. So any way you want to find that. Then if you want to find the expected value, just do what I said, right? Multiply these all up, add them together. So my expected value here is going to be 0 times 36 out of 100 plus 1 times 48 out of 100 plus 2 times 16 out of 100. Sorry for the small space. This is like this is straight from an old IB question, so that's why they expect you to do this on a separate piece of paper. So this one didn't get that much space. You get 48 out of 100, 2 over 1, that's going to be 36, 32 out of 100. So it gets 50, 80 out of 100. So expected value is about 8 out of 10. Again, all that means is when we do whatever this is, like when we draw 2 balls at the back from random, we expect on average we get about less than 1 ball, less than 1 gold ball to be specific. So there's that. Now we go to part B. Now part B is a brand new question, so you can kind of throw most of this stuff out the window. Now they're saying 14 balls are drawn from a bag with replacement. So I'm not drawing 2 balls anymore, it's 14 balls. So we're drawing 14 balls from the bag without replacement. was replacement, sorry. Find the probability that exactly 5 balls are gold. So already, I'm thinking binomial question. We're drawing 14 balls. Like we had a whole problem. Now they're specifying something else, and it's exactly and at most. You're thinking binomial all the way. So it's exactly 5 balls. So this is, if you remember binomial, when it's exactly, that's binomial PDF. So we're going to define n, trials, probability, and then x is how many balls we're talking about. So let's bring our calculator out. So we're going to go to second distributions, right here, bars. Toward the bottom is binomial. Binomial PDF we're going to use. Now, number of trials is how many times we're doing this. So this is 14. That's what this is about. So 14 trials. Our probability of getting a gold ball. Now, it's not the expected value here. What it is, go back to the very beginning. There's only 4 gold balls and there's 10 balls in total. So probability of getting a gold ball is 4 out of 10. And then how many balls do we want? We want 5. Exactly 5. We hit paste, and we get that. So we're going to do binomial PDF of x equals 5. And then we get 0.206597. Remember 3 sig figs? So 0.207 will be your answer. So the odds of getting exactly 5 balls, if you draw 14 balls at random, is, if we're doing this 14 times, is about 21%. Find probability that at most 5 balls are gold. So the key thing here is to understand how to do at most 5. I always think like food. If I want at most 5 cookies, that's my limit. So it's x is less than or equal to 5. So to do that, we're going to do binomial CDF. Now we got lucky. This is the way binomial wants it. Binomial wants less than or equal to. We'll do some other ones later on where it's not like that. But binomial wants less than or equal to. So it was binomial CDF, where x equals 5. So just put that in our calculator. So we're going to go second distributions, binomial CDF, and then everything's the same. 14, 4 out of 10, or 0.4, and I want 5 again, at most 5. So less than or equal to 5, which is what thing wants. In that case, you get 0.48585 or 0.486. Remember, that's at most 5, so this is like, essentially you're adding, what you're doing here is you're going, probably that you have 0 gold balls, you get 1 gold ball, you get 2 gold balls, you get 3 gold balls, you get 4, and you get 5. That's all you're doing. You're adding every single possibility underneath 5. So that's what's going on. That's all that's going on there. At most 5, so you can get 1, 2, 3, 4, or 5. Add them all up, and you get this. So next one, our favorite type of question. Given that. So D is a given that problem. So we're doing binomial, and we still have a given that problem. Given that at most 5 of the balls are gold, find probably that exactly 5 balls are gold. Give your answer to 2 decimal places. Similar to the way you do given that, you want to do probability blank. A line is the given that line. So given that at most 5 balls are gold, so that's this. X is less than or equal to 5. Find probably that exactly 5 are gold, so x equals 5. Look at classic IB, 2 things we just did. Write down the formula. Remember the general formula for this in your formula sheet, which is this. B given A is you multiply times the second one, which is A, and it equals the intersection. So here, we do x equals 5, given that x is less than or equal to 5, which would be multiplied by the second one, x is less than or equal to 5, by the given that, equals the intersection. To me, this is always the hardest part. X equals 5, intersect x is at least 5. Something like that. So, this is our x, this is what we're looking for. This we know, we just did it, classic IB, 0.486. And then this we got to think about. What's the intersection of x equals 5 and x is less than 5? What do they have in common? Sometimes I like to do a number line for this. So I think it helps the idea. So we have x equals 5. So here's 5. There's my point. And then we have x is less than or equal to 5. So closed circle going this way. What's the intersection of these two? Well, it's just this guy. It's just 5. It's the only thing they intersect. This is the same. X equals 5. Hey, I know the probability. We did that up here. Classic IB. 0.207. You just divide those two. So I'm going to get 0.207 divided by 0.486, and we get 0.4259, or 3 sig figs, 0.426. So that's a given. That's a probability of, given you know there's at most 5 balls, what's the probability of getting exactly 5 balls? So that's the first one. That's probably the hardest example on this worksheet, because I generally give it so we could do it together in class. So that's why the first one's like that. Now let's go to some more straightforward ones. Again, all these are from old, not all these. This one specifically is from an old IB exam. You see how mostly these are kind of straightforward questions. A factory makes lamps. The probability that a lamp is effective is 0.05%, or just 5%. And a random sample of 30 lamps is tested. Already I see this question like, okay, it's either defective or not defective. We have 2 options, binomial. And they give you 30 lamps to test. So this is a binomial question through and through. Find the probability that there's at least 1 defective lamp. Given that, then given that question. So we'll hit one by one. First, find the probability that at least 1 defective. So at least 1 defective, think about it again, like food. At least 1 cookie means that's my lower bound. So x has to be greater than or equal to 1. Again, since at least it's a it's a binomial CDF question. But there's a problem here. Binomial CDF only works on less than, right? So this only works when it's like this. So you gotta remember how to fix it. If I have this, I'm going in the wrong direction. So the way you fix it is you do 1 minus it. When you do the complement of it, it fixes the sign, so you switch it. But remember, that is a greater than or equal to sign, so when you switch it, you always lose a sign. Because it's like, what's the opposite of this guy? Opposite of that guy is an open circle going in the opposite direction. That's how we got this from. So now we have this. 1 minus x is less than 1. But that's no good either. Remember, CDF only wants the equal to sign. When we do binomial CDF, it has to be an equal to sign. I don't have it. How do I get it back? You go 1 lower. So if your x is less than 1, we only use natural numbers. That means x has to be less than or equal to 0. So when you use whole numbers here, so you can't be less than 1, that means you have to be less than or equal to 0. That's what I'm going to put in my calculator. Again, sorry for the space. This is from an old IB question. So my calculator, I'm going to plug that in. So I'm going to go second distribution. Go to binomial CDF, because it's less than or equal to. Now my trials in this case, we have 300 lamps. That's my 30 lamps. My probability they gave us 0.05. And watch, you put 0.05. A lot of people mess up when they put just 0.5. And then my x value, it's going to be 0. Now I can put paste. Now remember, that's not the answer, because it's 1 minus that. So 1 minus this answer. And actually, I probably should have done it from the beginning. 1 minus that answer. And I get this. So my answer is going to be 0.78536, or 36 figs. 0.785. That actually reminds me. Up here, they didn't want 3 sig figs. They wanted 2 correct decimal places. So they actually wanted 0.43. That was the right answer. That would actually, we would have got marked off a point for that, because it said specifically 2 decimal places. So that's my answer, not this. Sorry about that. Anyway, when they don't mention it, it's 3 sig figs. So here's 3 sig figs. Again, I could have put that all into my calculator at once, and I should have actually. I should have spent 1 minus math. How I always go to math? Second distribution. Binomial CDF. Is it all saved? Yes, it is. Nice. And that would give me the answer if I didn't mess up straight away. Did I mess up? 1 minus. Because when I put math, I messed everything up. Second distribution. Binomial CDF. Enter, enter, enter. Now you see it. 0.785. So there we go. Next one. Another given that question, our favorites. Or actually IB's favorite more correctly. Given that there's at least 1 defective lamp. So probability, remember, given that's after the line. At least 1, like this. Wrong way. Find the probability that there's at most 2 defective. So at most 2. Remember, I was thinking at most 2 cookies, and that's my max. So like this. So this is what they want. They want probability that I have probability of most 2 if given that there's at least 1. So let's use the formula. Remember, the formula is this. and I always say this is the toughest part of it. So this is what I'm looking for. Probability of A is the probability of this. So second part, I should wrote that up here. X is less than or equal to 2, X is greater than or equal to 1, X is greater than or equal to 1, X is less than or equal to 2, and X is greater than or equal to 1. So that's my X. What am I doing? I'm going to do it right here. Since this X is greater than or equal to 1 equals probability of X is less than or equal to 2, intersection X is greater than or equal to 1. Now this, we just did that. That's what we did right here, right? We ended up getting this right here. So classic IB, answer here is 0.785. This guy, that's tougher. Now this is what like where I said I like to find the intersection of these two. What is this? What is that? So let's draw it. I have, here's 2, and I'm less than or equal to 2. Here's 1, and I'm greater than or equal to 1. Intersection is between 1 and 2. So I need to find probability of it being between 1 and 2. Basically of 1 and 2. So what I'm going to do here is probability of X equals 2 plus probability of X equals 1. I'm going to do both of those because that's what this is. It's saying basically find the probability between 1 and 2, right? Both odds are less than or equal to 2 or you're greater than or equal to 1. It's just 1 and 2. So I'll find those both probabilities. I can do my calculator. So it's going to be math, second distribution. I always go to math. Second distribution, binomial PDF. In this case, we have 30 trials, 0.05, 2, paste, plus, I'm going to do the second one, same idea, second distributions. See, now we're doing PDF. Hopefully I did PDF on the last one too. I'm pretty sure I did. Yeah, I did. 1. And I get that. I add those up. So this is going to be 0.5975400 times this. Kind of important here. You notice I didn't round on this one because actually it's in the problem I found this answer out. Over here I did use a rounded answer. So that's why. So like if I have that answer already, even though it's like 366, you use that. They don't want you to do 366 too soon. If it's in the current problem, you leave it the way it is. Then I just divide by this. I'm gonna divide that by my answer before, 0.785. And I get my X equals 0.7611975. So the odds of this happening are 0.761. So there we go. Gotta love those given that problems. So let's do some more like straightforward ones. We'll go with these faster. At a manufacturing plant, 35% of employees work night shifts. If 7 employees are each selected from the entire group at random, find probably that exactly 3 of them work night shift, at least 4 of them work night shift, less than 4 work night shifts. So again, straight out binomial question, right? They're saying here's 7 employees, exactly at least at most. That's the binomial question. This will be my N, this will be my P. Now for A, they want exactly, so it's binomial PDF, where X equals 3. Plug into our calculator. So second distributions, binomial PDF. So it's we have 7.35 and 3. 0.268. 36x. Done. B, less than 4. So we're doing binomial CDF. Now, less than 4 is this. You can't see it. There we go. B, CDF, less than 4 is this. Now, there's a problem here. Remember, when we do CDF, has to be less than or equal to. So it's less than. So how do I go down? Now, here's the thing. It's not pointing in the wrong direction. We have the right direction, so you don't do 1 minus. That's only when it's pointing the wrong way. So it is less than, so we're fine with that. All we do is lose 1. So it's the same thing as saying X is less than or equal to 3. So anytime you don't have the line, you just want to get the line back, you go down 1. You only subtract it from 1 if it's greater than, if it's going the wrong direction. So that's what I put in my calculator. So it'll be second distributions. I'm also down math again. That 7 trials, 35%. And in this case, my value was 3. Yeah, 3. So remember, 3 is the same thing as saying 0, 1, 2, 3. Add them all up. So that's why you get 0.8001, or just 0.8. So there's that one. C. At least 4. So again, at least 4 cookies. That means it's my lower bound. So x is less than or equal to 4. Now that has both. Now that's a problem because it's going the wrong direction. So this is where I go 1 minus binomial CDF of x is less than 4. Right? How do you make it point the proper way? You do 1 minus, but it had the equal to sign. Now I lost it, so I have to go down 1. So it'll be 1 minus x is less than or equal to 3. This is what I'm putting in my calculator, which is just 1 minus this guy, so 0.2. Right? Because I know less than 3 is 0.8, so 1 minus that's 0.2. Next one. Records show that 6% of the items assembled on production line are faulty. The random sample of 12 items are selected with replacement, binomial. Not probably that. None are faulty. So right here, binomial PDF x is 0. Right? I want none of them to be faulty. So this is your calculator. Second distribution, blah blah blah. Trials is 12. Probability is 0.06. X value is 0 in this case. I want none to be faulty. And I get 0.476. 366. Next one. At most one will be faulty. So again, at most one cookie means x is less than or equal to 1. 1's my high bound. And that's pretty fine. That's going the right direction. I put in my calculator. Binomial CDF. Nothing needed to be changed there. That's perfect. Sorry. Hit the wrong button. So that's me as CDF. Second distribution. Binomial CDF. So gotta put everything back in again. It saves it if it's the same one, but since I'm going CDF PDF, it switches. It doesn't save it. 0.06, very important. Make sure it's 0.06, not 0.6. And then 1. Hit enter and I get 0.840. Next one. At least 2 faulty. So at least 2 means, right, I want at least 2 cookies. So that's my lower bound. X is greater than or equal to 2. So again, that's pointing the wrong direction, so we got to fix it. 1 minus x is less than 2. Right, it was greater than, now it's less than, because I had to switch it. And then you have to go down 1, because it doesn't have an equal to sign, which I need. X is less than or equal to 1. So to put that into my calculator. Luckily some stuff will be saved there. So 1 minus second distribution binomial CDF. Oh, that's right. Oh, that's right. That is good. Hit enter. About 0.1160. 366. And then last one here for this one. Less than 4 will be faulty. So x is less than 4. Right? What's wrong with that? It doesn't have the equal to sign. So we got to go down 1. Only thing that's wrong with it. There we go. I can put that in my calculator. Don't have to do anything else. So binomial CDF. X is less than or equal to 3. Let's put that in my calculator. So second distribution. That. Blah, blah, 3. And then we get 0.996. So there we go. Next one. There's a 5% chance that any apple in a crate will have a blemish. If a random sample of 25 apples is taken with replacement, find the probability that exactly 2 of these will have blemishes, at least 1 will have a blemish, the expected number of apples that will have a blemish. So this is a typical IB like test question when they want to make sure that you know the basics. Be something to this effect. Okay, so we have a probability. 0.05. So don't forget, it's 5%, not 50%. We have 25 apples. That's our N. probably exactly 2 blemishes, so it's an exactly problem. So problem of PDF. So let's be binomial PDF x equals 2. Let's type that into our calculator real quick. So it takes me a lot more time to do this on the calculator on the computer than it is if I had it by hand, but same idea. So we have 25 trials. It is only 5%, so 0.05. I didn't move over. There we go. 0.05. Then the x value in this case is only 2. You get 0.231. Next one probably has at least 1 blemish. At least 1. So remember the way you do that? I always think at least 1 cookie. So x is greater than or equal to 1. 1 is my low bound. That's going the wrong directions, right? So TS point is greater than point. So I got to do 1 minus. So 1 minus x is less than 1. It had an equal to sign. I lost it. When anytime you flip, you lose it. Now I got to go down 1 because I need the equal to sign. So I'm going to plug this in my calculator. 1 minus binomial CDF. X is less than or equal to 0. Right, so you have to go down 1. Put that in my calculator. So 1 minus second binomial CDF. Everything's still the same. You know it doesn't save it in this case. 0.05 and then 0. And I get 7223 or 723. Right, so there's about 72% chance that you can have at least 1 blemish in a sample of 25 apples. And then here, the expected number of apples. So don't get freaked out by that. Expected number is the same no matter what we do. It's actually in your formula sheet also. For binomial expected number is just n times p. That's all it is. So the number you have times the probability. The number I have is 25. The probability is 0.05. Multiply those together, and you get the average number or expected number. Remember, average and expected value are the same thing. So 25 times 0.05. So 1.25. So about 1 apple for every pack of 25 will have a blemish. Both produced by machine varying quality. The probability that the given bolt is effective is 0.04. A random sample of 30 bolts are taken from this week's production. So again, you notice how they give you a probability and then give you a sample, an n. When I see those things, I'm thinking binomial all the way. If x is the number of defective bolts in the sample, find the mean and standard deviation of the x distribution. So let's do with that first. Remember, mean, like I just said, is just expected value. That's all it is. Those are the exact same thing. So if you want to find the mean, or it's its expected value. So the expected value, or the mean, is just n times p. That's all it is. It's a bad n. So in this case, I have 30 bolts, and I'm going to multiply by 0.04. Get my answer. So 30 times 0.04. Get 1.2. So that's the average or expected amount of bolts, defective bolts. Find a standard deviation. Now this is a little different. So let's look at our formula sheet. Now keep in mind we're doing binomial. So I have the formula sheet queued up here. So look at our formula sheet. Here's the binomial distribution stuff. So mean or expected value, n times p. Now, they don't have standard deviation, but they do have variance. The variance is np times 1 minus p. Now, remember, if you have variance, you can find standard deviation, right? Which one's bigger? Variance is bigger. So we just got to square root this to find our standard deviation. Let's go back to the problem. So if I want to find the standard deviation, we'll put variance here first. Variance is n times p times 1 minus p. So it's going to be 30 times 0.04 times 1 minus 0.04, so 0.96. Put that into our calculator. So I'm just going to get that answer we had, and it times that by 0.96. And I get 1.152. So I get the ugly one. I can't live with that. 1.152. And remember, that's the variance. I want the standard deviation. So standard deviation is the square root of variance, because variance is bigger. So it's the square root of 1 times 1.52. Now let's put that in our calculator. So second square roots. 1.07. Again, 3 sig figs. So there's our standard deviation of this. B Once you do the same thing, if y is the number of non-defective votes in the sample, find the mean standard. So it has non-defective votes. Well, probably that's defective is 0.04, so non-defective would be 1 minus that. This would be 0.96. So it's the exact same thing. Our mean would just be n times p, but in this case, 30 times 0.96. And then our standard deviation, we'll just skip a step and put square root of n times p times 1 minus p, where it's 30 times 0.96 times 0.04. If you notice on this one, that's the exact same thing. The variance doesn't change at all, right? So I'm plugging the exact same numbers in. So my variance will be exactly the same. Which kind of makes sense. If the odds, if the probability for being effective or non-effective are the same, well, not the same, but like related to each other, it's not going to change. The average, 30 times 0.96. 28.8. Yeah, I thought so. There's only 30 total, so there's 30 total, and the odds of getting defective is 1.2. This 1 minus that should get you 28.8. And there we go. Let's move on. So let's look at 8 here. 8's a combination, which we start doing more and more now. So we start doing a combination of different ideas. So a pentagonal and a square spinner are illustrated. The pentagonal spinner has 3 red and 2 green sections. Okay, square spinner has 1 red and 3 green. It doesn't tell me that. Complete the tree diagram below. So they want you to get red on the pentagonal spinner. So we're going to spin this first, then we're spinning this one second, I guess. So getting red is 3 out of 5, which means not getting red. Remember, that's what the little prime means, not red. Be 2 out of 5. When you do the square spinner, getting red would be 1 out of 4. Not getting red would be 3 out of 4. Same thing here, getting red would be 1 out of 4. Getting not red would be 3 out of 4. So there you go. Calculate probably that exactly 1 red will occur. So I just want 1 red. So remember, we want 1 red. So that's going to be red and not red plus not red and red. So red and not red would be this. Not red and red would be this. So 1 out of 4 I meant. So we'll get 9 out of 20 plus 6 out of 20. So about 15 out of 20. So odds of getting exactly 1 red is 15 out of 20. So that's, again, none of that was binomial so far. That's like a review of tree diagram. The pair of spinners is now spun 10 times. So we can do this 10 times. X the number of times that exactly 1 red occurs. So exactly 1 red occurs is that time. Okay, we know that probability. Write down the expressions for probability of x equals 1, probability of x equals 9. So again, we're spinning it 10 times. That's a binomial question. Now they made it binomial. They're like, hey, we're spinning 10 times. Here's your probability. Right, probability getting exactly 1 red. It's 15 out of 20. Right expression for p of x1. So I just got to write it down. I actually got to solve it. So it's binomial PDF of x equals 1. And actually, let's put it in my calculator. Let's just solve this real easily. So in my calculator, that would be, I'm going to go second distributions. So binomial PDF. Our trials were 10 trials. Probability is 15 out of 20. Figured it out in the first time. And then our x value is 1. So there you go. So that's a really small number. So it's about essentially 0. It's happening 0 times. That's why they just want you to write down that given answer. If you wanted p of x equals 9, it'll be binomial PDF of x equals 9. So we'll find that one out. See how? So again, that's essentially 0. That's like 10. That's 0.0002. 3 sig figs 0. That's what that is right there. So I'm going to do a little shortcut. I'm going to go up here. I'm going to change the PDF from 1 to 9. And that's an actual number. 188. 36 figs. Hence determine which of these outcomes is more likely. This guy. The more likely to get probability of 9. So this one's more likely of the outcomes. Px equals 9. 2. A manufacturer finds that 8% of items produced from its assembly lines are defective. During a floor inspection, the manufacturer randomly selects 10 items with replacement. Find the probability that the manufacturer finds. First of all, why is he replacing it? Doesn't that kind of defeat the purpose? But beyond his bad management skills, we'll still do this problem. So that's my n. N is 10. Probability is 0.18. They want to find the probability at 1 defective, 2 defective, at least 2 items affected. So again, 100% binomial question. I see one, exactly 2, or at least binomial question. Right, this will be binomial PDF of x equals 1, binomial PDF of x equals 2, and then this one, at least 2 defective, again, at least 2 cookies. So it's like that, so it's going the wrong way, so you gotta fix it. Do 1 minus, but when you flip it, you lose a line, so then you have to go 1 below. Like that. I'm gonna put this all into our calculator, and then we're done with this problem. So you guys can do that. We'll move on. Next one, binomial random variable x has a probability distribution given by this. So this is a probability distribution function where x equals 1, 2, 3, 0, 1, 2, 3, and k is a constant. Find k. So if you remember this one, it's a binomial distribution problem. So that means I want to make a table for this. And I might just skip this one all together because this looks like to me a long one. So this is my x, and this is my p. I got 0, 1, 2, 3. So if we plug in 0, that's just going to be 0. That's actually not going to be 0, sorry. If you plug in 0 for x, we're going to get 3 to the 4th to the 0, which is 1. And then 1/4 to the 3rd. So cube it all, I get 1/4 to the 3rd. So 1/64. If I plug in 1, so we're just plugging 1 into all that, so I get k, oh, there's a k on top, sorry. K times 3/4 times 1/4, 3 minus 1. I think I realized how long this one was going to be when I put it on the worksheet. So I get 3/4 times 1/16, so I get 3/64. So it's 3k over 64. I plug in 2, so I'm going to get 9, and I'm going to get 1, so I get 9k. We'll go a little faster now, over 64. Plug in 3, so that's going to be 3 to 27. That's just going to be 0. So 27k over 64. So that's my probability distribution. And then what we're going to do is set it all equal to 1, right? So k over 64 plus 3k over 64 plus 9k over 64 plus 27k over 64 equals 1. Multiply everything by 64. I did not give enough space for this problem. All the bases cancel. I get k plus 3k plus 9k plus 27k equals 64. 64. So I get 10k, 30 plus 10, so 40k. Divide by k, divide by 40, and k equals some decimal. So 64 divided by 40. And I get 1.6. This is like just a straight up review question. I think the standard deviation might be a thing. No, this is like totally just review. I guess you could do a binomial, but they don't really tell you. Probably the x is greater than 1, so that's going to equal to 1. So I'm going to add up all these. Actually, a little easier. I'm going to do 1 minus this guy. So 1 minus 1.6 over 64. That's great. Calculator. So 1 minus 1.6 over 64. This problem sucks. And I get 0.975. Okay. Find the expected value. Remember the way we do it? You multiply all these together and add them up. So I'm going to multiply 1 times, let's go 1 through here. 3 times 1.6 divided by 64. That's fine, because it's all, when you multiply, it doesn't matter what order. Plus 2 times 9 times 1.6 divided by 64 plus 3 times 27 times 1.6 divided by 64. And I get 2.55. That's the expected value of this guy. So there we go. And then now find the standard deviation of this distribution. So the way I would do that is on my calculator, I'll put L1, L2, find all one variable stats and get the answer. Now I have K's here and I really don't want to do that. I really don't. So I'm going to skip this one. Probably should skip that from the start. Next one, 40% of young trees that are planted will survive the first year. That is depressing. The botanical garden buys 5 young trees. That's not going to end well. Assuming independence, find the probability that during the first year, exactly 1 tree will survive, at most one tree will survive, at least 1 tree will survive. Right, so this is a classic binomial question. Probability is 0.4. Your n is only 5. Exactly 1 tree. Binomial PDF of x equals 1. Start calculating the answer in a second. At most 1 tree will survive. So remember, at most one I was thinking like at most 1 cookie. So like this, that's perfect for binomial. So binomial CDF, x less than or equal to 1, and then at least 1 tree will survive. So if I want at least 1 cookie, it's going the opposite way. That's pointing the wrong direction. So remember, the fixed wrong direction is 1 minus. Flip it, x is less than 1, but now you need the equal to sign. So 1 minus x is less than 0. Binomial CDF. Put those all into our calculator, get our answer. Let's move on. Save some time. This is much like the last one. It's actually way more just a review of another thing. So I'm going to skip that. What's the last one? A new drug has 75% probability of curing a patient within 1 week. So that's probability is 0.75. If 38 patients are treated using the drug, what is the probability that between 24 and 34 patients inclusive will be cured within a week? So what's going on here? Is there n? The inclusive part makes this a little funky. So they want between 24 and 31 inclusive. So think about this. So we want our x to be between 31 and 24. Right? But inclusive. So how do we find this part? Easy. Binomial CDF, x is less than 31. Right? So that'll give me from 31 all the way down. Right? That's all CDF means. We're going 0, 1, 2, all the way to 31. How do I do this part? Like how do I only get 20? I can't do in between. So what we can do is we're going to subtract off binomial CDF of 24, basically. Binomial CDF, x is less than 24. Right? Because remember, what that is 24 from here all the way down. There's one problem with this. So that's the way I would normally think about it. It'd be CDF 31 minus CDF 34. What happens there is we get what's left over. This minus that would get 20. This right there. One problem. We want inclusive. If I subtract this off, I lose 24. So what I'm actually going to do is 23. Right? So that would make, so again, I want to keep 24. So I'm going to do 23 instead. So when you subtract off 31 minus 23, you do this guy minus this guy. Let's erase the 30, that right there. What are you left off with? Well, you're left with this guy. So that's to me the trick to this one. So it's a little funky because it said inclusive, but that's the trick. So we're going to do binomial CDF of 31 minus binomial CDF of 24, where my P is 75 and my N is 38. So let's put that in my calculator real quick. So second distribution, now they're all less than, so we're all good. Binomial CDF of 38, 0.75, 75, and then I want 31. Then I'm going to subtract that from, well, I'm going to subtract from that, should say more properly. I'm a CDF 38, 75, but 23 because I want to keep the 24. Hit enter, and when I do that, I get 0.837, which is the correct answer. And that's a lesson worksheet.